In the second item, on the second test, we have a diving board that has a whole variety of various loads being applied. Two different distributed loads, one uniformly, one linearly varying, a concentrated force, and a couple at the tip of the so-called diving board. And so, of course, we'll start with a free body diagram, and then we got to get our unknown reactions. That's what we've been asked to find. And so, pin support, roller support, we haven't labeled these yet, so let's call them A and B. Call them anything you like, doesn't really matter. And we've got at the pin reaction two independent ones, AY and AX. At the roller, we've got a perpendicular force on the horizontal plane. And so that's a properly done free body diagram. Now we can apply our equilibrium constraints. We've got distributed loads, and we'll handle those by effectively going to the centroid of the area of that load. And so those centroids are located such that triangles at the 2/3, 1/3 distance, so 4 feet away from A, and then of course the rectangle's in its middle, so it's 5 feet because of the total length of 10 of it. Right? And that gives us then all we need to properly write the equilibrium equations. What's some moments about B to find A, taking clockwise is positive, so we have plus 400, and then we have plus the triangular load, so 1/2 of the height times the base of 6 times the moment arm of 10 plus 4, or 14, and that's all going clockwise around BY. AY is written that way too, so plus 10 times AY. And then the other distributed load is going downwards, so that creates counterclockwise about B. So I'll have 10 kips per foot times 10 feet for a total of 100, with a moment arm now of 5 feet with respect to B, and then minus 30 times 5, oops, not 5, 4 feet for the point load of 30. That all has to be set equal to 0. And we find out that AY is equal to a minus 20. And that minus sign just means that although we guessed it was going up, that it is not. That AY is going downwards at 20 kips. That's one of them. And then we could do the trivial one here too, and we need to. No forces in the x, we only have AX that equals 0, so therefore now is the trivial one. And then we could sum forces in the y, but why do we want to do that? Because if we made a mistake on this other one, that'll carry over. So let's instead sum moments about point B. Let's take, about point A, we already did point B. We'll take clockwise as positive again. We get 400 plus 1/2 of 10 times 6. Now the moment arm is only 4, and that's clockwise. AY and AX go through that point, they're out of it. We've got the distributed load of 10 times 10, and a moment arm of 5, but this time that's going clockwise about the point of interest, so that's a plus, and then we have a plus 6 times 30, and then we have a minus 10 times BY. Set that equal to 0, and we find out that BY is equal to 120 kips acting upwards. We have plus out of this equation, so as shown, so it's acting upwards. And then we'll do a check of our math by summing forces in the y. Let's take up forces positive. We have 1/2 of 10 times 6, or that would be 30, acting upwards. We have AY acting downwards at 20, and then we have the 10 times 10 of the distributed load in the middle, minus then the 30, and plus the 120 for BY. Right, so the 30s cancel out. I have a minus 120 here, plus 120. That equals 0. That's what it's supposed to. And we have done that math correctly.